Hello, everyone. Thank you for being here and listening to my talk and looking at my poster. My name is Jordan Young, and I am a student at Stony Brook University. Today, I'm going to be talking about convolutional neural network models for ordinary chondrite petrologic type classification. So the rationale for this project is to explore the role of deep learning in the planetary and exploratory sciences and to help develop statistical models that can assist scientists in those fields. In order to apply deep learning to some problem, you need three things. You need training data, you need labels, and you need some sort of statistical framework or model. I'll go ahead and talk about all three of those things right now. To gather training data for this project, we used a suite of ordinary chondrites spanning petrologic types 3 through 6, or all the metamorphic grades for ordinary chondrites. Specifically, training data was gathered by making mosaics of each meteorite thin section, which were created by stitching together 4 times reflected light microscopy images. Then, training images were selected from the mosaic image at random. 2 training data sets are available. Both are grayscale. One is 512 by 512 pixel squared, and the other has 256 by 256 pixel squared images. So for labels, we used the ordinary chondrite petrologic type number. Ordinary chondrites have metamorphic classification numbers known as petrologic types. They can be classified into groups 3 through 6 based on several petrologic criteria. And this classification system provides a super easy way to assign labels to images, and you can see what the quantitative labels look like on the right. It's a 4-element array with a 1 in the column that represents type 3. So type 3's column is the first, type 4 is the second, and so on. And finally, the model that we used is a convolutional neural network, as the title would suggest. It's a statistical model that accepts image tensors as inputs and outputs predicted labels. So just a quick results page. What you see here are several different model architectures that we've trained, all pretty high accuracy scoring, but the best one is 4C5D, which has both a training and validation accuracy of 90%, meaning that if you put in a reflected light image of some meteorite thin section that's 512 by 512 pixels or 256 by 256 pixels, then 90% of the time it will accurately guess or accurately predict its label, its petrologic type, which is really cool. So there's a lot of future work that needs to be done, including developing a better labeling system, adding more samples to the training set, using genetic algorithms to uncover better network architectures for this problem, and to apply more deep learning models for different problems in other planetary science contexts. Finally, I would just like to acknowledge everyone here for advice and sample allocation and funding. Thank you.